Hi, folks. We're in Module 3, Novice Problem Solutions, 3 and 4 this time. Let's get to it. Let's pull up our worksheet for the problems. Let's start with Problem 3. In Problem 3, we are using what we've learned with probability and trying to put it in the context of real problems. So we have a situation where several people are asking questions about the success or failure of some franchises that they're going to open up, fast food franchises, and in Fort Lauderdale, Florida. So the first question they have is, if you assume that the probability of the success of a franchise after 3 years of operation, you need to give it some time to gestate, so to speak, is 50%. What is the probability that after opening 12 stores in Fort Lauderdale, all 12 stores will be successful? In other words, they will all still be in operation. Well, I give you a hint that this is a binomial distribution, and it is. It's the probability of success of a certain number given a certain number of trials that has a certain probability of success for all trials. So it's highly unlikely that all 12 are going to succeed if you've got a 50-50 chance that an individual store will survive. So how do we calculate that? We use the binomial distribution function. Here you see it. The binomial distribution function is asking, what is the probability that 12 trials, 12 successes will occur in 12 trials with a probability of 50%, and the false is tells it that I don't want the cumulative probability of 1, of 2, of 3, or 4. I want what is the probability of 12 out of 12 succeeding, that one thing to happen. So here's our probability function, and you can see that's a very, very small number. There's only about a 2 in 1,000 chance, 2 in 10,000 chance that all 12 stores will remain in operation. The next question asks something a little different. It says, what is the probability that fewer than 6 stores will be open after 3 years? What is fewer than 6 stores? Well, that's 5 stores, or possibly 4 stores, or 3, or 2, or 1, or even 0 stores. So we have to accumulate all those probabilities. In this case, the false that we had here, where we weren't accumulating probabilities, is going to become a true if we go over here to this particular function. So this tells us that what we're looking for is success of 5 given 12 trials with probability of success for any trial being 0.5, and we want to accumulate it. Probability of 0 plus 1 plus probability of 2 plus 3, 4, and 5. And here's our answer. It's about 38.7%. There's an alternative function called the binomial distribution range, and what this function allows us to do is to create a similar sort of probability function where we have 12 total trials, we have a probability of 0.05, and I want the range from 0 to 5. I want 1 plus 2 plus 3 plus 4 plus 5. It's an accumulation, and you can see that what happens is we get the very same number. Now, the next problem says that the annual revenue is estimated to be 1.5 million to 5.2 million. And additionally, there's no way of knowing if any one of those values is going to be higher than the other. Anytime you don't know what the result is going to be in a distribution of outcomes from one value to another value, the only fair thing to do is to assume that they're all the same. And this is why this is the uniform distribution, because that's what the uniform distribution says. All possible outcomes between 1.5 million and 5.5 million are equally possible. And I want to know what is the probability that the outcome is going to be 3.75 or less. Okay, so really what I'm talking about, here's our distribution, a uniform distribution from 3.5 all the way over to 1.5. How do I do that? Well, we have to manipulate that because we don't have a function for it. We say, I'm going to take the area from D34 to D33. D4 to D33 is this entire area here below 1.5 to 5.5. What does that give us? 4, right? And then I'm going to divide that into the difference between D35 and D33. D35 is the value and D33 is the low area. So it's this area here. So I'm taking a proportion of the entire area versus this little area here. And that's 4 divided by, I think, 2.25. And of course, that gives us about 56.25%. The last one asks us to estimate what the probability is of some arrivals. We have an arrival process, and you know from your reading, arrival processes are often described by the Poisson distribution, which is a discrete distribution. And the Poisson distribution has one parameter, one thing that describes it, and that's the average arrival rate. For us, that average arrival rate is 200 per hour. So the question is, what is the probability of 175 or less, 174, 172, 33, 37, all those probabilities added up, and it being 175 or less when the average is 200. So we go to our Poisson distribution. The first element, the first argument is the value that we're interested in, x. The mean is the average arrival rate, 200, and we use a true here because we want the cumulative for that. And we can see that the probability of 175 or less is about 4%. Kind of surprising, isn't it, that it would be so low? But believe me, that's the case. All right, let's take a look at problem 4 now. In problem 4, what we've got is a potential outcome for the amount of time required to complete an uncertain task, this installation of this instrument called a confusatron. And what we're trying to do is trying to get an idea of what the probability for these this outcome, the average of all the possible outcomes and their associated probabilities is going to be. So in the first exercise, what we do is create this distribution and say, all right, let's randomly select 100 values from this distribution, a distribution where there's a 15% chance of 35, a 55% chance of 60 hours, and a 30% chance of 100. And let's look at that data. So in the problem here, as you can see, what we've done is I have taken, and I'm using a VLOOKUP, by the way. I've told you to use a VLOOKUP for that. The VLOOKUP is going to take a value, a random number. That's what this thing is here in the adjacent cell. It's something called a rand. A rand is a number between 0 and 1 that's uniformly distributed. So if I recalculate this particular spreadsheet, I'm not going to do it because it messes with the presentation. But if I do that, all these numbers will change. These are all rands here, and every rand has its own unique value. So the VLOOKUP says, take this value, go over to a table. Where's my table? My table is these 3 columns, and look up the value that's associated with my random number. So for example, 0.984552 is larger than the largest value here, so it's going to return 100. What about the next? It just changed. Let's try this one. Why did this return a 60? Well, it took this random number, 0.627, went to this table. It found that 6.27 is between 0.15 and 0.7, and therefore it returns the top value of 60. Okay? We simply have to tell it where the table is. In this table, the intermediate column doesn't do anything for us. It's this number and this number, or these columns and these columns that are important to us. The top value of a table like this always begins with 0, and then we start adding the probabilities of what can happen. 15%, then 55% adds to 15 to give us 0.7, and then I don't have to go any further than that. So what we've gotten is 100 outcomes, and I've calculated the 100 outcomes average here, and you can see it's very close to what we would expect. This is the theoretical outcome, which is 0.15 times 35, 55% times 60, and 30% times 100. This is theoretical, but our outcomes randomly selected because we used the same distribution are pretty close. If we had had a lot of numbers there, it might have been exact, or much closer to being exact. All right, that's the end of the solutions for problems 4 and 5. Excuse me, 3 and 4.